Okay, well, our final talk of the day is by Angelica Simonetti, and it's on Z-mod 2Z equivariant smoothings of cusp singularities.
Okay, thank you everyone for being here. Can you hear me? Okay, thanks for the invitation to speak. This will be a very light talk, so you can consider it like a nice ending of this afternoon. And so, okay, the first thing I'm going to define is cusp singularity. So some of you already know what cusps are, but I'm going to start with the basics and define singularities. So consider P in X, the germ of an isolated singularity surface. Then let's say pi from x tilde to x is the minimal resolution. And E is the exceptional divisor, so the pre-image of the singularity. Then definition, P and X is a cusp singularity. If E is either one irreducible nodal curve, rational curve, so is small as a rational with one node, or E is a cycle of smooth rational curves. So, or E is a cycle of smooth rational curves meeting transversely. When I say a cycle, I really mean a cycle. Okay. And then, in this case, E is the union of a bunch of irreducible components. Notice, so there are some conditions on the self-intersections. So if n is bigger, larger or equal to 2, then, well, I'm considering the negative of the self-intersections have to be greater or equal to 2 for I, and at least one of them has to be greater or equal to 3. So there is some specific index, at least, say J, one index for one component. And this comes from the fact that you have a minimal resolution and the intersection matrix related to E has to be negative definite. So you must have these conditions. Okay, so, well, let's see an example. Okay. So an easy example is an hypersurface in C3. So one of such hypersurfaces is the following. This sits in C3. And then, okay, this is going to be a sketchy way of showing you how to resolve such a thing. So, well, you start with a singularity. P, you blow up once, and you get a cycle of 3 curves, but there are still singularities. So you're going to have 3 type A singularities. In this case, they're going to be an A1 singularity, an A2 singularity, and A4 singularity. So what do you do now? Well, you blow up again. Now we know how to resolve these A-type singularities. We're going to have a bunch of -2 curves. So at the end, you're going to get something like this. Well, let's see. -2 for the A1. Okay, so the -2 curves come from the resolution of this. Okay. Some quick properties and notation and language. So I will denote the self-intersections as the cycle of integers. So P in X. And the cycle of integers determines the cusp singularity up to analytical type. So either giving you the list of integers or the cusp is exactly the same. And then, well, the multiplicity well, this is going to be 2 if the self-intersection of E is equal to 1, and then it's minus E squared otherwise. But then this is not super important. And then the number of components in the cycle is the length of the cusp. So, okay. Maybe I'm going to use this one. So one nice property of cusps is that they come in pairs. So every time you have a cusp singularity, you will have a dual cusp singularity. So what's a dual cusp singularity? There are many ways to see this duality. The easiest one is in terms of the cycle of integers. So I'm going to start there. So if P and X is a cusp with cycle of integers A1, and then possibly some 2s, and then A2, all the way to say AL, and then a bunch of 2s. This can be, the number of 2 here can be 0. So, and then AI is at least 3. So basically I'm subdividing every integer which is at least 3, and then I'm counting the 2 in between. So this, I'm calling this B1, the number of 2 here, up to BL. Then if I want to write down the cycle of the dual cusp, say P prime, X prime, well, that's going to be P1 plus 3. And then sum 2, V2 plus 3, all the way down to VL plus 3. And then there's a bunch of 2. And then now you can guess the number of 2's you have here is going to be related to the A's here. And that's going to be A2 minus 3. And the last one is A1 minus 3. So A2, A3, A4, and then the last one is the first one. Okay, so this is very easy if you want to compute dual cusp singularities, but does not give you a sense of why they're dual. Well, let's see. I'm not going to give you the details, but there are other 2 ways, I guess. Well, one is there is a construction by Hirzebruch that gives a bijection between cusp singularities on one side and hyperbolic matrices, or equivalence classes of hyperbolic matrices in SL2 Z. And now using this bijection, if A is the matrix associated to P and X, then A inverse is what you're going to use to construct the dual cusp. In terms of the link of the singularity, so P and X and P prime and X prime share the same link. But with opposite orientations. So there's also nice quotient constructions that you can use to see how these are dual, but I'm not going to describe that right now. We'll see how time goes. So now in terms of the examples, okay, I have another example here, but in terms of the example that I gave you before, and then there's this other one, let's see what the dual cusp is here. So, well, we have the cycle of integers. We can compute this thing. Well, this thing, let me check the numbers. Okay, so this is what you have if you compute the dual to this cusp. And this is an example of, this is in C4. This is a complete intersection in C4. And okay, if you compute the cycle associated to it, you get this. What do we get if we try to compute the dual? Well, we get -4. There's a minus everywhere here. We get this. Okay, so, well, one comment that I can make is that every cusp singularity which appears as an hypersurface is going to look like this, with P with some exponents, P, Q, and R. Every complete intersection is going to look like this, cusp, which is a complete intersection. And there are equations for a case wherein the embedding dimension is equal to 5. It's the Pfaffian of a matrix, but that's it. We don't have equations for higher embedding dimensions, as far as I know. Okay, and then you can see, well, here the embedding dimension was 3, and the length is 10. Here, well, the length is going to be 3. Let's say this is T. Here, the embedding dimension was 4. The length was 8. Here, the length is going to be 4. And then you have to believe me, the embedding dimension here is 10, and here is 8. So basically what happens is that the embedding dimension and the length of the cycle exchange roles. So you get the embedding dimension of 1 as the length of the dual cycle. Okay, so that's always true. Can I use this board?
Yeah, but everybody's taken in the most important information.
Yes. Yeah, go ahead.
The other part you wrote that dual cusp singularity share the same link.
Link, yes.
What do you mean by link?
So you consider the germ of the singularity. You take a ball intersecting the germ of the singularity, and then you consider the boundary. And that's the link. It's three-dimensional. Is that right?
Another way of saying it is that that matrix corresponds to two, well, it has two quadratic numbers, irrationalities, as I know that. Yeah, and that gives rise to a toric picture like that, with this continued fraction, an infinite continued fraction. And you take the dual lattice of that.
Okay. Yeah, so just to recap properties of dual cusps. Well, let's say E is a cusp singularity. E is the cycle. I'm going to use E for the cusp as well. Then the dual to D is the dual. So the dual to D is E. Dual of the dual is the original cusp, which makes sense. And then, as I said, the embedding dimension equals the maximum 3 and the length embedding dimension E depends on the length of D. Okay. So one question that you can ask is, why cusp singularities? And so when one possible answer is that they appear at the boundary of the compactification of a modular space, the modular space of surfaces of general type. So if you look at the boundary, you see cusp singularities and their quotients by Z mod 2Z actions. And of course, not all of them appear there, right? So only those which are smoothable, which admit a smoothing. So it is interesting to ask whether or not a cusp is mutable. And for cusp singularities, the answer is no. So now I have to apologize because I discovered that I pronounced this name incorrectly, but I won't try to correct because I'm going to make a mess. There's this theorem by Luyenda. So I think it's 81. And then Ross, Arkin, and Keel, 15. It basically says that P in X, a cusp singularity is mutable if and only if D, which is the dual cycle to the cusp, okay? Dual to P in X sits as an anti-canonical divisor. On a small surface. So what we have is an anti-canonical pair. And we discussed this morning, so we know what they are. So, and this is nice because instead of now checking whether or not a singularity is mutable, you can check if this exists. And this can be done algorithmically. It's easier. You start with a minimal pair, and then maybe start to blow up until you get, if you can, until you get the right self-intersections in the right length of the divisor. So the idea of this talk, okay, everything I'm about to say is the work of my PhD thesis. So it's work with Paul Hacking mainly. And what we were trying to do is do the same, but not for cusp singularities, but for cusp singularities with azimuth to Z action. So something similar, but with this action involved.
All right. Give an example of a non-smooth. I'm just trying to envisage what one that's not smooth will look like. Or alternatively, like, you know, a cycle which doesn't go on a smooth fractional surface.
I have
an elliptic curve of degree 10. If you take the cone over an elliptic curve of degree 10, if you tried to smooth that, it would have to be a Delpexo surface of degree 10. Yeah, so it's not exactly answering the question, but it's essentially the same.
You have to.
So like an elliptic curve with self-intersection -10 or something.
Yeah, generally everything below embedding dimension 9 is mutable. So you have to go.
You have to work very hard.
Yeah.
I sort of look at this thing like, you know, I can make a lot of fancy on it with the device.
But I do have an example of a cusp which is mutable but not equivariantly, which is with this azimuth to the action.
Yeah.
Okay. So before I can discuss the theorem, I have to talk about Luyenda pairs for a second, just to give you some reference. So. So let's remind ourselves what a Luyenda anti-canonical pair is. So an anti-canonical pair is a small projective surface together with well, let's say an anti-canonical divisor. And this is not exactly the definition, but this is what characterizes them for me. So D is either an irreducible curve with a node. So where D is either irreducible rational curve with node, or a cycle of smooth rational curves. So D looks exactly as the exceptional resolution, exceptional divisor of a minimal resolution of a cusp, especially if we impose that D is negative definite. Okay, we're only going to focus on negative definite Liouville pairs, anti-canonical pairs. So we say the anti-canonical pair is negative definite if the matrix associated to D, the one with the intersections, is negative definite. This, as you can imagine, will impose the same conditions on self-intersection as we had before. So every self-intersection, the negative has to be at least 2, and at least one of them has to be at least 3. Okay. A couple of examples, and then we're ready to go. So examples. Every toric surface with its toric boundary, it's a Liouville pair. So an anti-canonical pair. Then there's basically 2 operations you can do to get other possible Liouville pairs. One is what it's called a toric blow up. So you blow up one of the nodes of your cycle. So you have your cycle of, say this is the example where you have more than one component, but you blow up one of the nodes. So okay. And in this case, you still get some, well, you do get another anti-canonical pair. So you get I prime D prime, where D prime is the inverse image of D. Okay, so you take the new divisor, you created a new divisor, and you're considering that in your new cycle. Or instead of blowing up one node, you blow up an interior point, one of the smooth points on the cycle. Okay. So point on E. So again, now you're blowing up one of these points. And now you don't take this divisor when you consider the new Luyenda pair. So the new pair here, D prime, is the strict transform, okay? So interior blobs change the self-intersections. Toric blob change the length of the cycle. And basically you have a bunch of minimal pairs and everything else can be constructed either with a toric or an interior blob.
You should say these are both log crescents.
Sorry.
Blow-ups.
Yes.
So KY prime plus D prime is the pullback of KY plus P.
Okay. Yes.
The reason
Sorry, I'm lost. Yes.
You made a blow up.
Yeah. Yes.
And then you ignored the exceptional curve.
Yes.
That's the strict.
That's right. Yes.
The reason for doing that is because it's log crescents.
Oh, yes. Sorry. Yes. That's correct. Sorry. Okay. Let's move. So now that we have Luyenda pairs, we move to, now we have to consider the azimuth to Z action. So now the question is, which kind of azimuth to Z action are we considering? Well, the one that comes from a specific type of involution. So consider a cusp singularity, some involution. I on a cusp singularity. Next, we say it's antisymplectic. If there exists nowhere vanishing to 4 omega holomorphic such that when I pull back using I get minus omega. So this is the kind of involutions we're going to consider. And plus, we're also going to always assume the involution is fixed point free away from the singularity. So and now the first question you can ask is, can we characterize cusp singularities which admit such an involution? So how do they look like? The answer is, well, a cusp singularity in X admits an antisymplectic involution if I don't say it, it's always fixed point free and so on. If and only if the exceptional cycle has the following properties. So two properties. The first one is the involution is not allowed to fix any node. It can only fix two components. Okay, so I has not fixed any node. It fixes two components setwise. So in particular, the length has to be even. Okay, so we're only considering even cusps of even length. And then the second is these two components, so the self-intersections of these two components has to be even. Okay, so these are the two conditions. So here there's one way, this is an if and if, right? So there's one direction that's quite easy. If you do have the involution, you just need to check that these two are true. And then what we did, well, if we had these two conditions, we actually produced the involution using, there's a quotient construction for cusp singularities, and we use that. Basically, what Miles was describing before, so you can use the matrix to get eigenvectors, and then you have this cone, and then you can construct the cusp singularity from that. But anyway, so we got the involution quite explicitly. Okay. And then one comment.
Exactly two components or?
Exactly two components, yes. So you're going to have, I usually draw it like this. You're going to have two components which are fixed, and then you can think of the action, at least on the divisor, as a reflection. Okay. So a very quick comment. Is that, well, we'll call these cusps symmetric because they're nice and they're quite symmetric, at least in self-intersections. So and then if a cusp singularity is symmetric, then the dual cusp is going to be symmetric as well. So if one has an involution, the other one is going to have an involution as well. Prime next prime is symmetric. There's a natural way to start with one involution and get the one for the dual. Okay. Now we go to, now it's a very similar story with Liouville pairs. Now we'll define an involution on the Liouville pairs, we'll characterize them, and then we'll get everything together. So let's define it. The involution on the Liouville pair anti-canonical. It's, again, I'm going to use the same name, so antisymplectic. If it reverses the orientation of T. And this is true even for cusp singularities. One way you can think of the antisymplectic involution is if you look at the exceptional cycle, is going to, so the induced involution on the minimal resolution is going to reverse the orientation of the exceptional cycle. So this is what happened here, what happens here. And then again, we're going to consider only those which are fixed point free away from the divisor. So now, same question. So can we characterize Liouville pairs admitting such an involution? The answer is yes. So yeah, Liouville pair, anti-canonical pair. Admits antisymplectic involution. If and only if there exists a sequence of contractions. Okay, so maybe you start with YD and you start contracting pairs of -1 curves. Until you get to P1 cross P1 with its toric boundary. So there exists sequence of contractions with pairs -1 curves such that the involution here goes down. So it is preserved, it is respected at every step. That's why we contract pairs. And then we get to a fixed involution here. So such that at the end, it respects involution. And at the end, we get the involution J from P1 cross P1 with its boundary. Thus, it takes, say, ZW to 1 over Z minus W in non-homogeneous coordinates. So again, one side is very easy. It's easier if you do start with P1 cross P1 and you manage to blow up pairs of curves. Then what you get? Well, you get a Liouville pair with an antisymplectic involution. You just keep your involution and you lift it.
Delta is the 4 lines.
Yes, yes, sorry. Yes, sorry, yes. Yes.
And what's your involution?
So Z, I'm assuming. Okay. So it fixes two components, and then it swaps the other two, and there's going to be 4 fixed points here. So on the components which are fixed, there's going to be 2 fixed components on one and 2 fixed points on one and 2 fixed points on the other. Yes. Okay, so again, the non-easy part was to start with YD with an involution and then show that you can always find this pair of curves to contract all the way down to B. Oh, here I'm assuming and this. So the length of the cycle is at least 4. We want to go down to, but well, yes. 2 is an easy case because you have equations, so we were interested in any greater or equal to 4. Okay, and then we showed basically that there was never the case where 2 minus curves in the same orbit, so the one you want to contract, intersect, because in that case you would not be able to contract them at the same time. So. Okay, so now we're ready for the main result, yes. Just to give you, just to give you an example of a symmetric cusp, the one we had before, 4, -4, -5, -5, -2. This would be a symmetric cusp, right? Because, well, these two match, and these are the ones which are interchanged, and these two are even, so that agrees with our definition. So this would be an example. Okay. Okay, so the main result is, remember, we wanted to find smoothings, Z to Z equivariant smoothings of cusp singularities, which will correspond to equivariant Q-Gorenstein equivariant smoothings of the quotient singularity. So if instead of the cusp singularity together with the Z to Z action, you just look at the quotient, you get a new singularity, which is called quotient cusp singularity. And it's taught and rational. And then you can ask when that is mutable. Well, that's the same as asking when the cusp singularity is Z to Z equivalently mutable.
I mean, to contextualize, those are that's a main class of log canonical
Mm-hmm.
Quotient
of cusps.
And to determine which is smoothable has to do with understanding the boundary of the moduli space of surfaces.
Yes.
Maybe source of general type and so on.
Exactly.
And then that's something that I don't know if you were going to say this or not. But
I think I said it at the beginning, but
I see, and I was thinking of it.
But that's fine.
Yeah.
Yeah. But exactly, yes. So okay. So the theorem, well, we have a sufficient condition. So if we have the next cusp singularity with an involution, if the dual cycle T again sits as an anti-canonical divisor a surface Y, and so far it's what we had for cusps, normal cusps, but such that YD admits an anti-syncretic involution that extends the one that we have. Remember, if you have an involution here on E, say on the cusp E, then this will induce an involution on D. So the involution on YD is an extension of what you expect on D. Okay, so that extends the one induced on the tubular neighborhood D by then P in X is sigma to Z equivariantly. So it's very similar in concept to what we had for cusps. And as an example,
but it's definitely not an if and only if.
We don't have, so far, we think it is an if and only if, but we don't have a proof for that. But it should. So again, so if you consider this cusp, okay, this is D, okay. So E was P in X is the cusp you want to find the smoothing of, and it's associated to E. Then you look at the dual. You get D. Now that is Z-mod is equivalently smoothable if you can construct a Y, D, such that this is like this. Okay, so what do? Well, you start from P1 cross P1 with the historic boundary. And then what do you want to do now? Well, you want to do a bunch of interior blow-ups, right? So how many? Well, 10 here, and then 4 and 2 here. So and every time you blow up pairs, so you blow up like points in the same orbit, here, and so on and so forth. And so every time you lift your involution that you have here, and then at the end, what you get is YD, where D is equal to this. And using this reasoning, we were able to show that if so every cusp with a bending dimension or multiplicity less or equal to 10, if it's okay, every symmetric cusp of embedding dimension or multiplicity when it makes sense, less than or equal to 10, is equivalent is mutable. And yes, we basically used the theorem, so the sufficient condition. So everything we needed to do is, well, we found, well, the case of multiplicity 2 is done by hand because you have equations. And then for 4, 6, 8, and 10, we used 1, 1, 1, and 3. Minimum, not in the sense of the minimum of the program, but in the sense of very low self-intersections, and show that these 3 pairs over here and these 3 pairs over here admitting an involution. And then everything else can be obtained from these 6 pairs. So if these 3 Rienger pairs admit an involution, then everything that can be obtained from them, again, admits an antisymplectic involution, which corresponds to, well, every cusp of length of multiplicity less than 10 has to be equivalent is mutable using the theorem. That makes sense? Okay. And why did we stop at 10? Okay. Last comment. So, no. So we stopped at 10. Because for 12, there are some cases where we could not construct the pair, the anti-canonical pair. So for n equals 12, all but 8 cusps are 0 to 0 equivalent to this mutable. There are these 8 cusps for which we could not construct the corresponding Rienger pair with an antisymplectic involution. So we don't know. If we had an if and only if statement, we would be able to conclude, but so far we don't. And one example is the following. So 12 is the embedding dimension. So it's going to be the length of the dual cycle. So this is one of the 8 cases where, well, you can find a Rienger pair, but it's not going to, there's no way you can construct an involution. And the way we show that is using the theorem we have about characterizing Rienger pairs with an antisymplectic involution. So if we had, by contradiction, suppose we have an antisymplectic involution, then we should be able to go all the way down to P1 cross P1 in an equivariant way. And that's not possible. That can be checked with a computer. So, okay. Now we would like to show the entire conjecture, but this is what we have so far. And I'll stop.
Are there any questions?
So I'm not quite sure if you address this small ambiguity.
Okay.
So when you say singularity, we're talking in local analytic geometry.
Yes.
So if I have, for example, an affine algebraic surface with a singularity, then it would be perfectly possible that as an analytic singularity, this has an involution.
Okay.
But the given affine thing does
Okay.
not. So I mean, you know, you're drawing, when you draw things that lie on an algebraic surface, means you've chosen a model in algebraic geometry
Okay.
for this local analytic setup.
Okay. Yes. Sorry. Yes. Sorry if there was an ambiguity, but yes.
And you know, if you draw that picture, then I can't help in my mind dividing it by 2, noting it's at the bottom as I have a -1 curve, and I can contract that -1 curve all the way up to the top to get an A2 singularity.
Okay.
You know, I doubt if, you know, you can reconstruct that. You can reconstruct the double covering, because it would have to be a very, very singular branch curve.
Okay. Okay.
But
I see. Yeah, but yeah, what I think when I say that it's not possible to construct an involution, I really mean an involution on the whole D, so the whole Y, the whole surface. And yeah.
Any more questions?
Can you look at, I mean, so can they have more automorphisms if they want to?
I've only considered Zimotuzi actions so far. So, yeah.
Actually, I think if you have other actions, the only thing you get is.
I'll need to turn you up, Paul.
I'm sorry.
Okay.
I think you can see if you have any other group acting, you know, the only thing you can do is sort of rotate the cusp and then just get another cusp as the quotient. So Z2 is Z2 is essentially the only case to consider.
Thanks.
More questions? Let's thank the speaker again.